everyone, welcome to this explainer. Today, we're diving into something that impacts almost all of us at some point, yet it remains a profound engineering mystery to most. We're talking about medical imaging. You might think snapping a perfectly clear picture inside the human body is just about building a higher tech camera, right? Well, the fascinating and honestly mind boggling reality is that perfect medical imaging is actually a relentless battle against the fundamental laws of physics. So, let's get right into it. Here's our roadmap for today. We'll start with the quest for clarity, then look at physics and the scintillation limit, move on to math and the Fourier prism, explore the cost of discontinuity, balance things out on the resolution seesaw, and finally synthesize the final image. All right, part 1, the quest for clarity. When it comes to medical imaging, the stakes are incredibly high. For doctors and patients, a blurry image isn't just annoying, it can literally be the difference between a misdiagnosis and a life-saving early intervention. We absolutely rely on these machines to give us razor-sharp views of the invisible. But here's a startling truth for you. Perfect medical image clarity is physically and mathematically impossible. It sounds crazy. Your doctor's million-dollar machine is basically forced to guess, but it's completely true. The central conflict we're exploring today is exactly why this perfection is impossible, and more importantly, how brilliant engineers basically cheat these unbreakable laws to save lives anyway. Moving on to part 2, physics and the scintillation limit. Before a computer can even look at an image, a physical machine has to detect a signal from the patient's body. And boom, this is exactly where our unavoidable problems begin. When a single, precise, infinitely small gamma ray hits the detector's scintillation crystal, it doesn't just stay a tiny, perfect point. No, it instantly spreads out into this broad, diffuse pool of light by the time it reaches the back. Right there, in a fraction of a millisecond, perfect spatial resolution is totally destroyed. This messy physical process actually has a name: scintillation. It's basically what happens when a crystal absorbs high-energy incident radiation, like the gamma rays emitted during a scan, and re-emits that absorbed energy as a flash of lower-energy visible light. It's a beautiful physical conversion, for sure, but an incredibly frustrating one when you're trying to capture a sharp image. Take a look at the theoretical ideal versus what reality actually gives us here. We desperately want that precise spike, a sharp, exact location of a biological structure. But reality hands us that wide, blurry bell curve. Because the light spreads out into a broad footprint across the tubes, this system literally has to guess its origin. It relies on statistical centroid positioning, which is just a fancy way of saying it mathematically guesses the center of that light puddle. Because of this estimation, exact positional certainty is permanently lost before the computer even receives the signal. The physical blur is just locked in. So, the crucial takeaway here is that we're starting with a flawed, fuzzy dataset, which leads to a very natural question. If physics inherently blurs the image at the hardware level, can math just step in and fix it? Let's leave the messy physical world behind for a second and step into the pure theoretical realm of mathematics to find out. Part 3, Math and the Fourier prism. This is the stage where the computers take over, using something we can picture as the Fourier prism. You know how a glass prism splits chaotic white light into a clean rainbow? Well, the Fourier transform takes the messy, complex periodic signal from the scanner and brilliantly deconstructs it. It breaks the signal down into simple, easy-to-manipulate low, medium, and high-frequency waves. It's basically the structural DNA of our signal. By doing this, engineers can finally start isolating broad anatomical structures from sharp edges and separate both of those from random background noise. To get a clear medical scan, doctors desperately need to see sharp borders. Think of the exact edge of a tumor or the fine boundary of an organ. Mathematically speaking, a perfectly sharp edge is represented as a square wave. But remember, Fourier math only gives us smooth, rolling waves. So to build those sharp vertical edges, the math requires us to stack multiple wave frequencies, which we call harmonics, right on top of each other. It works in steps. Step 1 starts simply with just one fundamental harmonic, giving you a base rolling curve. By step 2, we add more odd harmonics, 3, 5, 10, maybe 20 of them, and the wave really starts looking more like a sharp square. But step 3 is where we hit a massive mathematical roadblock. To recreate an instantaneous, perfectly vertical edge, it requires infinite high-frequency components. And real-world computing simply cannot process infinite harmonics. It would literally take forever. So the computer is eventually forced to just stop calculating. That brings us to part 4, the cost of discontinuity. Since we can't compute to infinity, we have to cut the math short. This creates a truncation artifact, specifically known as the Gibbs phenomenon.
Because we have to eventually truncate or chop off the Fourier series instead of calculating out to infinity, the math essentially freaks out right at the point of that sharp discontinuity. It inevitably creates an overshoot, specifically about a 9% overshoot, which is immediately followed by a rippling effect called ringing. You can see it wobbling right there in that peak. The wave physically wobbles just because we had to cut the math short.
So, why does this matter for you or your doctor? Well, look at this clinical comparison. On one hand, you have real anatomical data, sharp biological boundaries and high contrast interfaces, like dense bones sitting right next to soft tissue. On the other hand, you have artificial ringing, these Gibbs phenomenon halos and star artifacts created purely by mathematical truncation. The clinical danger here is immense. If the computer isn't incredibly careful, doctors could mistake these mathematical artifact ripples for actual anatomical features, or even disease. Or, on the flip side, the ripples could totally obscure a small, real tumor.
Let's move to part 5, the resolution seesaw. Okay, so our hardware physics gives us blur, and our software math gives us ripples. How on earth do we get a usable image out of this? It all comes down to the resolution seesaw. Everything in modern image processing relies on this delicate balance. If you try to push down high-frequency noise to make the image smoother, you inevitably elevate the blur, which completely destroys your sharp edges. But if you try to minimize the blur to get crisp, sharp resolution, you heavily amplify the statistical noise, making the image a terribly grainy mess. You just cannot perfectly have both.
Different software filters handle this trade-off in completely different ways. A high-pass filter, like the ramp filter, gives you high, sharp spatial resolution, but at the painful cost of high noise. A low-pass filter, like a Gaussian filter, heavily blurs the image, giving you very low resolution, but creates a super smooth, low-noise picture. It is a strict seesaw trade-off. But check out that bottom row. Restoration filters like Wiener and Metz, these are designed to offer an optimized middle ground. Let's look at exactly how they do it.
Notice that bright diagonal line going straight up? That's our baseline, the ramp filter. This fundamental high-pass filter is designed to multiply the amplitude of each frequency component by its frequency. It perfectly preserves those sharp edges we so desperately need. But the catch is brutal. It disastrously amplifies high-frequency statistical noise, which naturally dominates the upper end of the spectrum. If we only used a ramp filter, the final medical image would be completely unreadable because of the chaotic grain. And this is where the sheer genius of modern imaging engineering really shines. Enter the restoration filters like Wiener and Metz, which you can see seeking out that middle ground. These advanced filters don't just blindly cut frequencies. They actually attempt to mathematically model the imaging system's inherent hardware degradation. They act as inverse filters at lower frequencies to actively restore that degraded spatial resolution caused by scintillation, literally fighting back against the physics. Then, right before the high-frequency noise gets completely out of hand, they apply a roll-off curve to suppress it. They are actively trying to cheat the seesaw, masterfully balancing blur and noise to output the absolute best theoretical image possible.
Finally, part 6, synthesizing the final image.
Think of this entire journey as a continuous, beautifully complex relay race. Step 1 is physics. Scintillation creates an inherently blurred and noisy physical signal right at the hardware level inside the detector. Step 2 is math. Fourier transforms brilliantly deconstruct this messy, degraded signal into frequency components that we can actually manipulate. And finally, step 3 is processing. Advanced software filter functions manipulate these frequencies, artificially rebalancing the lost spatial resolution against the systemic noise. It's an incredible, continuous dance to compensate for the fundamental physical limits of light dispersion. So, what should you really take away from this explainer? Well, there are 3 inescapable truths, fundamental principles of image formation that engineers have to battle every single day. First, the scintillation limit. Perfect theoretical spatial resolution is physically impossible because light inevitably disperses in the detector crystal. Second, the cost of discontinuity. Because we can't compute infinite math, we must always account for truncation and those resulting Gibbs phenomenon ringing artifacts. And third, the filter trade-off. Clear images require perfectly balancing the resolution seesaw, intentionally sacrificing some sharpness to keep noise from ruining the picture. Which leaves us with this final, thrilling question to ponder. If scintillation inherently limits our physics, and truncation strictly bounds our mathematical processing, how will the imaging engineers of tomorrow cheat these seemingly unbreakable laws to see the unseen? Will artificial intelligence learn to perfectly predict and entirely remove the blur? Will quantum sensors completely bypass scintillation in the first place? It is an absolutely fascinating frontier. Thank you so much for joining me on this explainer today. I really hope this journey helped illuminate the hidden complexities behind the screens. Keep learning, keep asking questions, and I'll catch you next time.